Hi everyone, this is 9702 AS Physics past paper questions from 1.3 and 1.4. Here under 1.3 we have errors and uncertainties. We have two types of errors, systematic errors and random errors. We are also going to distinguish between precision and accuracy. And we are also going to solve some problems based on absolute uncertainty and percentage uncertainties. Here, types of errors. We have two types of errors, systematic errors and random errors. Systematic errors are caused by mainly due to the fault in equipments, like zero error, incorrect calibration, and sometimes also due to the reaction time of the experimenter. How it can be minimized? By improving the apparatus, you can reduce the systematic error. Random error, the causes are mainly due to mishandling or improper method. So like parallax error or incorrect usage of the apparatus, and sometimes also due to the environmental factors like sudden change in the temperature. How it can be minimized? By repeating the measurements. Okay. Here are some differences between systematic errors and random errors. Based on definition, systematic errors are consistent and repeatable. Random errors are unpredictable and vary. What are the causes? Faulty equipment or improper calibration. Here, mainly due to human errors and sudden change in the environmental factors. What would be the effect of systematic errors in your experiment? You can see all the measurements are skewed to one direction. And whereas in random errors, it can cause a spread around the true value. For example, if you have 9.81 is the true value, 9.81 Newton per kilogram is a true value, your values will be spreading around like 10.5, 8.7, 9.9, something like that. Okay, it will be spreading around the true value. How can you detect systematic errors? It is difficult to detect because when you're using 2-3 instruments in your experiment, it is difficult to locate which instrument is faulty. So you need to find one by one. You need to check the zero error of each instrument, and then you have to start over all again. Random errors, it can be detected by analyzing multiple measurements. So you repeat the experiment and then you find the average. Here the correction can be done. You repeat the experiment as many times you can, and then you find the average. Here in the system, under systematic errors, if you want to minimize, you eliminate find the error source first of all, where the instrument is faulty, then you eliminate that, then repeat the experiment all over again. So moving on to accuracy and precision. So if you can see from this diagram, all the values, there are 5 data points collected in an experiment. All the 5 data points are close towards the target, okay, towards the true value. So this is highly accurate. Here, the values are not accurate. Actually, accurate is here, but the values are precise. So when you repeat the experiment, the same error has occurred, but still it's more precise, but it is not accurate. Here, the values are close to the accuracy, but they are not precise. They are spread over, okay? They have spread over. So it's accurate, but not precise. Here, it is not accurate and not precise, okay? So if you want to plot a graph between the number of readings and the real value also, you can see like this. Precise and accurate, precise but not accurate. It is precise but not accurate. So you can see the real value here and it is not accurate. So here, imprecise but accurate, imprecise but not accurate. Okay. Difference between accuracy and precision. Based on definition, accuracy is close to the real value of the measured physical quantity, whereas precision is the closeness of repeated measurements. So even though your value is wrong, but if you keep on getting like 5.9, 5.7, 5.8, 5.9, 5.9, so you are repeating the same value again and again. So you are more precise. For example, if the actual value is 6.5, but you're not getting 6.5, but instead you're getting 5.8, 5.7, 5.8, 5.6, 5. So you are not close to the accurate value, but the value, the readings, what you're getting again and again, it's more reliable. So precision is close to the repeated measurements and accuracy is close to the real value. If your real value is 6.5 and you are getting 6.45, 6.51, 6.46, 6.52, then you are close to the accuracy. Measurement. An accurate measurement may not be precise. A precise measurement may not be accurate. How to improve? We already told systematic errors. Sorry, minimizing systematic errors will improve accuracy. Precision, minimizing random errors will improve precision. Okay, minimizing random errors will not improve accuracy. Minimizing random errors will improve precision. Okay, depends upon, accuracy depends upon precision, but precision doesn't depend upon accuracy. What is the importance of accuracy? It ensures ensures the measurements are correct, and precision, it ensures the measurements are reliable. Uncertainty. How do you define uncertainty? It's the range within which the true value is expected to lie. For example, you are measuring the length of the table, and the table is like 150 centimeter. Okay, so we cannot say that this would be the exact 150 is the 50 centimeters, the exact value, exact length of the table. If you see in your meter rule, we can measure 0.1 centimeter. This is the minimum measurement we can make using a meter rule. So usually we will write like this: 50 centimeter plus or minus 0.1 centimeter. So it could be, the value could lie between 150.1 centimeter, or it could be 149.9, am I right, centimeter. So the value is lying in between these two. So this is the range, the maximum range and the minimum range. So the correct value lies in between these two. So this range gives you the uncertainty. All instrument comes with uncertainty. So it's not actually an error. All instrument comes with this range. Okay. So here, now, for example, you take a cylinder is shown here with 9.5 centimeter. Actually, the length of the cylinder is 9.5 centimeter. So that is the X value. And because we are using a meter rule to measure this one, the smallest possible measurement it can do is 0.1. So it could be 9.5 centimeter plus 0.1, which is 9.6 centimeter, or it could be 9.4 centimeter. Okay, this is the absolute uncertainty for this measurement. What is fractional uncertainty? Fractional uncertainty is like, this is the formula you use. So you have to delta X. What is the absolute uncertainty divided by the original value? So it's like 0.1 divided by 9.5, which we will get as 0.011. So the percentage uncertainty is going to be the fractional uncertainty times the 100%. So which we will get this as 1.1 approximated to 1%. So, okay, this is the fractional uncertainty times 100% will give you the percentage uncertainty. Okay, now, whenever we are using uncertainty in expressions, if your expression is of the form V is equal to 8AB by C, because here multiplication is there, division is also there. Whenever you have that one, you don't bother about the constant. Do not include the constant, because the constant is not going to contribute anything towards the uncertainty. Only these are the variables, okay? These are the variables in your formula. Only based on the variables, the uncertainty will be, all the uncertainties will be added, okay? Just because A multiplied by B, do not multiply here the uncertainty values. The fractional uncertainty value shouldn't be multiplied. Instead, they all should be added here like this. So this is the actual formula. If you want to find the percentage uncertainty, you just add all the fractional uncertainties of all these variables. Here, C is in denominator. Do not do anything like, you do not divide this value. You add that uncertainty to here, and then you multiply by 100% to get the percentage uncertainty for this quantity. Then if it is in the form of power, whether it is A, here I have shown A cube plus B square, even if it is going to be A cube B square, it's going to be the same formula we have to use, like A cube plus B cube. Look here, if it is a to the power of 3, you have to multiply the power with the fractional uncertainty. Like here, b square, you multiply the power 2 here with the fractional uncertainty, then multiply by 100% to get the percentage uncertainty for this one. Even if it's going to be a cube b square, here it is addition, the operation is addition, still you have the same. Here if it is multiplication, still your formula will remain the same. So only thing is we are going to find how these variables contribute to the uncertainties. That's it. So the value, the formula remains the same. Next chapter 1.4 is scalars and vectors. We have already come across scalars and vectors in O level itself. So scalars and vectors, definitely you know that they have magnitude, no direct. Scalar has only magnitude, no direction. Example, distance, mass, speed, and so on. And vector has both magnitude and direction, displacement, weight, velocity, momentum, acceleration. Okay, so many things. Scalar quantity is a one-dimensional quantity, like the mass is a one-dimensional quantity. Then the distance is a one-dimensional quantity. Here in vectors, like you have one-dimensional, two-dimensional, and three-dimensional. Two-dimensional, like if you want to measure this velocity, if your vector is like this, and you are going to resolve it along the x-axis and along the y-axis, so you have a two-dimensional vector quantity. Three-dimensional vector quantity, suppose if there's a drone and it's at a certain axis in space, depending upon the x, y, z. Okay, so this will give you the three-dimensional displacement from a reference point. So vector quantities can be one-dimensional, two-dimensional, and three-dimensional. Okay, change in scalar quantity will give you change in, whenever there is a change in magnitude, that will also lead to change in the scalar quantity. Whenever there is a change in the magnitude or change in the direction or change in both, that will give you a change in the vector quantity. The last one is when a scalar quantity is mathematically operated by another scalar quantity, it gives a scalar, like a scalar multiplied by a scalar or a scalar added to it with a scalar, it will give you a scalar. However, when it is operated by a vector, scalar times vector or scalar plus vector, it gives you a vector quantity. Depending upon the dot and the cross product of vectors, okay, dot and cross products we are not doing in physics, maybe in mathematics you may be doing that one. Depending upon that, the outcome of the two vectors, whether you multiply or you add, if there are two vector quantities, it may give you a scalar or it may give you a vector. Okay. Addition of vectors. The basic addition of vectors we have already seen in O level. So for example, if this is 10 Newton, this is minus 10 Newton, and this is also minus 10 Newton. Your answer is going to be minus 20 Newton because they are both of the vectors are in the same direction. And if this is minus 10 Newton and this is going to be plus 10 Newton, your resultant is going to be 0 Newton. If this is going to be 10 Newton and if this is going to be, for example, 3, it's very small, is it? 3 Newton. So it's going to give you 13 Newton. And here, if this is 10 Newton, oh, I'm sorry, this one is minus 10, minus 3. So minus 13, yeah. Okay, and here this is plus 10 and this is minus 3 Newton. It's going to give you 7 Newton. Okay, this basic addition of vectors, if they are in the same direction, we know. Addition of vectors, if it is like this, okay, when they are not in the same line, but they are in the same plane, we call this as coplanar vectors. Coplanar vectors, vectors that lie on the same plane. If it is like this, how your resultant should be. Whenever there's a vector, we call this part as the tail and this as the head of the vector. So you can see here, the head of the first vector, V1, is connected to the tail of the second vector. Then it started from here, okay? It started from this point. The vector is heading this way and it is then subjected to V2, okay? So one object is subjected to two different forces or two different velocities, something like that. So V1 and V2. So here it started from here and it ended here. So here you just connect this, but the direction, be careful, it should be from the starting to the finishing point. Okay, that is your resultant. Okay, so can you see here? It's going in the clockwise direction, like from right to left, and your resultant is also going from right to left. If you see here, V1 and V2. So head is connected to the tail of the second vector. Then it started from here. So then you connect it like this. That's your R. So you can see your vectors go again clockwise from left to right. So your resultant also goes from left to right. Okay. This is very easy. If you get vectors like this, it's going to be very easy because you can use Pythagoras theorem also to find the resultant. And you can join, suppose this is a starting point, and here it's like this. This is the resultant. And the R can be found by using V1 square plus V2 square. Okay. Subtraction of vectors is nothing but addition of subtraction of vectors also follow the same addition rule. Only thing is you have to be very careful. For example, if you take this one, we have already seen this one where the resultant is going to be like this. And this is nothing but V1 plus V2. Okay, this is the resultant vector. Here, V1, but the V2 is in the form of minus. So here it started from here, the head, the tail, and here. So it should come like this. This is the starting point. The vector is heading here. The head of this is connected to the tail of the second vector. The second vector is minus. So it should start from here to there. So this is the resultant. But be careful whenever you write, the resultant is equal to V1 plus minus V2. Or you can simply write V1 minus V2. Okay. The next one is the angle between two vectors. I think you know this, how to find the angle even from O level. So it's like when there are two vectors, you can use either tan, or if you know the hypotenuse, either you can use sine or cos. Okay. Resolving a vector into two components. Whenever you have vector like this, because all the time we cannot be having vectors along the x-axis, along the y-axis. So if sometimes, no, not sometimes, most of the times we will be having vectors like this. In this case, what we will do, so we are going to resolve this into the x direction and the y direction. Okay. So here, x and y. In case if you know any of this angle, okay, if you know any of this angle, either this angle, if you know how this vector is tilted to the x-axis with what angle. If you know this angle, then it is going to be easy for you to find the components. So here, it's going to be the one along the x-axis is going to, because this theta, this resultant is adjacent to the x-axis. Okay, the angle theta is subtended to the x-axis. So here it's going to be the x component is going to be, or we can say the horizontal component. The horizontal component is going to be 7 times cos theta. Okay, 7 times cos theta. And for the vertical component is going to be, vertical component is equal to 7 times sine theta. Okay, so you follow this formula whenever you want to resolve a vector. Yeah. Yeah. So here it's going to be 7 times cos 12. This is for the x component. And for the y, it's going to be 7 times sine 12. Okay, that would be the velocity in the y direction, 7 times sine 12. Along the x component, along the x direction, the velocity is going to be 7 times cos 12. So these two together will give a resultant of 7 kilometer per hour. Okay, that's the meaning. Okay, next we are moving on to some past paper questions. What calculation produces a vector quantity? Vector quantity means it should be a scalar, a vector and vector. Which one is giving a vector and a vector? Current, time is a scalar. So I hope this one, Let us check. Work done. This is a scalar, 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 scalar. So, okay, so it's B. Okay, a vector quantity minus a vector quantity is going to definitely give you a vector quantity. We are not doing any cross product or dot product, so don't worry about that one. Here we are just making a simple normal subtraction. So addition and subtraction of two vectors is going to give you only vector quantity. A thermometer can be read to an accuracy of 0.5 degrees C. This thermometer is used to measure a temperature rise from 40 to 100. So there are two values here, 40 to 100 degrees C. So the difference is like 100 minus 40, which is going to give you 60 degrees C. Sorry, 60 degrees C. Okay, so here, and this is plus or minus 0.5. So how will you do this one? So for the initial reading and the final reading, so you have like, okay, this is the initial reading and this is the final reading. So here we have like, shall we keep this as theta 1, theta I, and this is theta F. So we have here delta theta F divided by theta F plus delta theta I divided by theta I will give you the uncertainty value. So here delta theta F is the same 0.5, 0.5 divided by final temperature is 100 plus 0.5 divided by 40. Okay, am I right? So it's going to give you, let me calculate. So it's 0.5 divided by 100 plus 0.5 divided by 40. Then this value, you multiply by 100. It's equal to, I'm getting 1.75. So actually we are, I think this one. Okay, 1.75%. Okay. What is the scalar quantity? The one with the magnitude only. Quantity, this is wrong. Only vectors can be represented in two components. Quantity, that no, wrong. It requires a number and a unit to represent a scalar quantity. Is quantity without direction. Yes, quantity without a quantity without direction is correct. That is scalar. Okay. The value of quantity X has a percentage uncertainty 2%. The value of quantity Y has percentage uncertainty 4%. The value of quantity W is calculated from the values of X and Y. Okay, so there is something like this. W is equal to either XY or X divided by Y or X plus Y. We do not know whether it's X, Y or X plus Y or something like that. Okay, so W is related to X and Y. So we have to find based on this one. The value of W has a percentage uncertainty of 8%. So we have this two. This two should give you 8%. So if you do 4 plus 2, it will not give. If you do 4 times 2, XY, 8. But we are doing we are doing uncertainties here. We cannot multiply. We have to only add. So uncertainty is 4 plus 2, 6. So what can we do? It can be like, if I square this one, X square Y, because X square Y will be 2 times 2 plus 4. But that one is not given here. But this is also correct. Then what is given here? Okay, let us go by this one. XY is going to be 4 plus 2. No. This is going to be 2. We cannot use. Again, this is going to be 4 plus 2. Wrong. Which is going to give you 6. This is going to be X is 2. So 2 on top. And sorry. 2 plus, not 2 plus 2 times 4. Am I right? So it's going to be 10. Okay, it's wrong. So obviously this one, let us check. Y is 4 plus 2 times 2. Yeah, it's 8%. Yeah. So this is the right answer, D. Moving on to the next question. The measurement of a physical quantity may be subject to random errors and to systematic errors. Which statement is correct? Systematic error cannot be reducing. No, it can be reduced. It can be reduced. No, it can be reduced. So cannot is wrong. A systematic error results in a different reading each time the measurement is taken. No. Precision, random errors will give you different values. So this is also wrong. Random errors are always caused by person taking, not always. Not always. Sometimes it can also be due to environmental factors. So that is also wrong. Random errors can be reduced by taking the average. Yes, this is correct. It can be reduced by taking the average of several measurements. So correct. So D. The Young's modulus of the material of a wire is to be found. The Young's modulus E is given by the equation E is equal to 4FL divided by pi d square x. The wire is extended by a known force and the following measurements are made. Which measurement has the largest effect on the uncertainty in the value of the calculated Young's modulus? Okay, so they have given the value of L, D, F, X. These are the variables. Now what they want is which measurement has the largest effect? Obviously D square, because all the uncertainties you are just going to add 0.002, 0.001 and 0.02. Only this one in this formula, whenever you are using, if you see here, you are going to use delta F by F plus delta L by L plus 2 delta D by D plus delta X by X. This is how, this is X. Okay, this is how we have formula. So all the other uncertainties will be just only added only once. But here, the diameter uncertainty will be added twice. So that is going to contribute more. So it is B. Two physical quantities combined together as a product can produce a scalar quantity or a vector quantity. Which product of two quantities produces a scalar? A scalar multiplied by another scalar. No. Which product of two quantities? Okay. So the product should give you a scalar quantity. Okay. Force times displacement is going to give you work done. Mass times acceleration is going to give you force. Pressure times area is also going to give you force. This is resultant force. Resultant force. Velocity times time is going to give you displacement. So this is a vector. Displacement is a vector. Force vector. Work done is a scalar. So it's A. Okay. A hollow cylinder, which is open at both ends, has a radius 3 plus or minus 0.1 centimeter and a length of 15.0 plus or minus 0.1 centimeter. What is the value with its absolute uncertainty of the surface area of the cylinder? Okay. Surface area of the cylinder is 2 pi RL. Okay. So now they want the surface area with the absolute, okay, with its absolute terms. So let us find 2 pi RL. First of all, let us find the surface area is equal to 2 times 3.14 times 3 times, that is the radius, and the length is 15. So that is going to give 2 times 3.14 times 3 times 15. 282.6 centimeters square, approximated to two significant figure, 280 centimeters square. Then come to the delta SA. by SA is going to be, here only these two variables are going to contribute. So delta R by R plus delta L by L. So which is going to be delta R is 0.1 by 3 plus 0.1 by 15. So which is going to give 0.1 divided by 3 plus 0.1 divided by 15, 0.04. This times, if you want only that absolute uncertainty, you multiply this by the surface area. So I'm getting 0.04 times surface area is 280. So that times 280, 11.2 centimeter. So actually it should be 280 plus, because we have to round this off to one significant figure. So 10 centimeter. Yeah. So it's 8. Yeah. Okay. So uncertainties round off to one significant figure. So that's why it's 10 centimeter. A copper pipe has a true diameter of 42.03 millimeter. This is the true value. But a builder is measuring the diameter 5 times. Okay, these are the measurements shown. Okay, 48, not accurate, not accurate, not accurate, not accurate, not accurate. Okay, so are they close to each other? 48, 47, 48, 48, 47.99, near to 48. Okay, so they are precise but not accurate. Yes or no? They are precise but not accurate. Yeah, here. Okay, so the next one. Two forces, each of 10 Newton, act at a point P as shown. The angle between the directions of the forces is 120 degree. What is the magnitude of the resultant force? Here you can use the law of parallelogram, which states, sorry, yeah, this will be the resultant. So here it states that the resultant is equal to square root of P square. If this is P and this is Q vector, P square plus Q square plus 2PQ cos theta. Let us check. So it's going to be 10 square plus 10 square. This is 10. 10 square plus 10 square plus 2 times 10 times 10 cos 120. So if you plug in these values, you will be getting 100. Cos 120. I'm getting 10. Yes or no? 10 Newton. So it's B. Okay. Two measurements for a solid sphere are shown. Okay. The mass is this one. The diameter is this 1.87 plus or minus 0.04 centimeter. These values are used to determine the density of the sphere. What is the percentage uncertainty in the density? So the formula for density is mass over volume. We don't have to calculate the density. We only have to find the percentage uncertainty in the density. Okay, now, but even though we don't have to calculate the density, we should at least roughly know because the diameter is given. So what would be the contribution of the diameter into the uncertainty, the percentage uncertainty? Here, the mass is the numerator, no worries, but the diameter comes because volume is like volume of sphere is going to be 4 over 3 pi r cube. But here what they have given is the diameter. So it's going to be 4 over 3 pi d by 2 q, which comes out as 4 by 3 pi d cube by 8. So here the constants, you put all these constants, you're going to get 4, 2, 6. So it's like pi over 6 d cube. Yeah, that's going to be our volume here. So the mass divided by pi over 6. So this constant is not going to contribute to the uncertainty, only d cube. So our value is going to be like this. The density formula will be like this. M pi over 6 d cube. Okay, for this, we don't want the density, only the uncertainty. So here, delta rho by rho will be delta m by m plus, okay? Even though this is in the denominator, don't divide. So it's going to be only d cube is going to contribute, not pi over 6. So it's like 3 times the power should be multiplied with the uncertainty of the diameter with the original value, which is 1.87, so d. Okay, so which will give us 0.1 divided by 32.5 plus 3 times 0.04 divided by 1.87, which is going to give us 0.1 divided by 32.5 plus 2 divided by 1.87. Percentage uncertainty multiplied by 100%. So we will get 6.72. Okay, so approximated to 2 significant figure is 6.7%. So it's D. Yeah, approximated to USF. Okay. The next one. A desk has a true width of 50 centimeter. Two students, X and Y, measure the width of the desk. Student X uses a tape measure and records the width. Okay. Student Y measures a meter rule and records a width of 51.4 plus or minus 0.1. Oh, this is not accurate. Okay, this one is accurate. Close to the value. Okay, 49.5 and 50 are close. So definitely what they want. Which statement about the measurement of student X is correct? Okay, so don't bother about the Y. You have to compare the X with Y. So definitely it is not less accurate. It is very close. 49.5 is so close to the true value. It is more accurate, but is it precise? It's not precise. You know, you see his values like going from 49.5 and plus or minus 0.5. Okay, so his value ranges from 49.5 to plus or minus 0.5. It's like it could be 50 or it could be 49. So he is having a range of value. So student Y, even though his value is wrong, 51.4, his range is like only 51.4. It lies between 51.5 to 51.3. Did you see the difference? Very small difference. Okay, so the range is very short for Y, but whereas the range is long for X. So it's less precise compared to Y. Compared to Y, it's less precise, but it is more accurate. So yeah, D. This is wrong. It is accurate, but it is not more precise than Y. It is less precise than Y. Okay. The diagram shows two vectors, X and Y, drawn to scale. If X equal to Y minus Z, which diagram represents the vector Z? Here, let us write like this. X equal to Y minus Z. What I'm going to do is Z is equal to, I'm taking the Z on the other side. It's going to be Y minus X. I brought the X this side, so it's good. So now Y is here, but I'm going to shift this vector to the same direction, okay, the same direction in this way. Okay, so it's going to be like, just invert this, like it's going to come like That's going to be my minus x, okay, in the reverse direction. So now it's going to be here like this. This is the starting. So y minus x. Actually, it is y plus minus x. So it's going to be z. This is your z value, which is a. A student determines the acceleration of free fall. Just okay. I'm sorry. Okay. A student determines the acceleration of free fall by using a small metal ball as shown. When switch S is open, the ball is released from an electromagnet and an electronic timer is started. The ball then falls vertically downwards. The timer stops when the ball hits a trapdoor. The student measures the distance PQ, okay, between the electromagnet and the trapdoor. This distance and the reading on the timer are then used to calculate the acceleration of free fall. Which statement about errors in the experiment is correct? Okay. Actually, imagine this ball is here, okay? Then it comes and hits the trapdoor here. Whenever we are making measurements, we always start from the center of the sphere. Yes or no? Yeah. So actually, let me draw it again here. This is PQ. PQ. But actually, we are not, the center of the sphere is not exactly at P. It is somewhere here. So let me put like this. Okay, the center of the sphere. And when it reaches the trapdoor, it is like this. Yeah. So actually, we have to measure only this distance. But we are measuring PQ. That's why there's an error. Okay. So how this can be reduced? Suppose if this distance is X. And if you see here, this distance, let me change the color. Here. Actually, this is the radius R. And there's one more radius here, R. So we can write PQ is equal to R plus X plus R. Yes or no? So what we have to do is 2R plus X, which is nothing but the diameter of the sphere plus X. Okay, this is the actual distance we should measure. The X must be the actual distance we should measure. So what we have to do, X is equal to PQ minus the diameter. So which one is correct? Which statement about errors in the experiment is with random error? It is not random error. It's not random error. The systematic error can be reduced by adding the diameter. No, we are subtracting the diameter. Look at this expression. We are subtracting the diameter. So the next one. The systematic error can be reduced by subtracting the diameter of the ball from the distance. Okay. So the diagram shows two coplanar forces, P and Q, drawn to scale. Coplanar forces acting on the same plane. So P, Q, what they want is Q minus P. So you invert this arrow, this vector. Okay, P should be going like this. So I'm going to bring, shall I put like this? In this opposite direction. Yes. Okay, P is here. Actually, this is minus P. So now Q plus of minus P. So it started from here. So, so that will be C, option C. Yeah, C. A student takes measurements to determine the constant acceleration of a model car moving from rest in a straight line. The measured values with their absolute uncertainties are shown. So the displacement, okay, acceleration is given. So you need to find A is equal to 2s divided by t square. So we have to find acceleration. So it's 2 times 16.5 divided by t square, 15 square. So the answer is going to be 2 times, I'm getting 0.15. So the now uncertainties will be delta A will be delta A by A will be only the S and T are the variables. So it's delta S by S plus 2 delta T by, so which will give us delta S is 0.1 divided by 16.5 plus 2 times 1 divided by 15 times, because we want the absolute uncertainty, you multiply by the acceleration. This is 0.15 meter per second square. So where we get 0.1 divided by 16.5 plus 2 divided by 15 equal to, then that multiplied by 0.15. So I am getting 0.02. Okay, that's all. 0.02. So here, this one. Okay, so answer is going to be 0.15 plus or minus 0.02 meter per second. So it's D. Okay, the next one. A plane is moving at a constant speed, which shows that the forward force and the backward force, the upward force and the downward force are all balanced. Okay, and it is being tilted to an angle through an angle theta. Which two equations must be correct? Okay, the forward force, thrust, weight, lift. Okay, so now, okay, here, let me show you the diagram. Look, so this is how it is. Yeah, weight. Okay, the upthrust, the forward force, the resistive force, and all together. So if you resolve this weight into two components, W, because this is theta, and this must also be tilted through theta. So this is W cos theta, and this is W sin theta. So here, there are two vectors in the towards the left direction. So W plus R sin theta. Sorry, R plus W sin theta must be equal to T, and L must be equal to W cos theta. So L must be equal to W cos theta, and T must be equal to, there are two forces in the left direction, so it must be R plus W sin theta. And that's why the plane is moving with constant speed. That means all these forces are balanced. That's why L equal to W cos theta, T equal to R plus W sin theta, which will be A. Yeah. Okay, a set of repeated measurements is made of a fixed quantity. An average of these measurements is calculated. What is the effect of averaging on the random error and the systematic error in the measurements? Random error and systematic error are both reduced. Effect of averaging. Averaging will not reduce the systematic error. Okay, random error and systematic error are both unaffected. No, wrong. Random error is reduced, but systematic error is not affected, because you're only doing the averaging. That will reduce the random error, but not the systematic error. Random error is unaffected, by systematic error is reduced. No, this is also wrong. Random error is not affected. Random error is affected. It is reduced. Okay. A boat is crossing a river in which the water is moving at a speed of 4 meters per second from left to right. Okay. In still water, the speed of the boat is 6 meters per second. The boat is directed at an angle theta to a line perpendicular to the river banks. The resultant velocity v of the boat is in a direction perpendicular to the river banks. Okay, so this is the resultant velocity. And here the water velocity is here. Okay, so it's like this. So this is 4 meters per second and this is 6. Okay, so here the resultant you can find, it's like this, so this is the hypotenuse. The 6 is the hypotenuse. So 6 square is equal to 4 square plus v square, or v is equal to square root of 6 square minus 4 square, which will give you 36 minus 16, 20. Square root of 20. Square root of 20 is around 4.5. Yeah, 4.47. Okay, 4.47, which is 4.5. So 4.5 meter per second. I think it's going to be A, because no other value is, so we can circle A. But still, if you want to find the angle, you can just go by, because we know theta And we know the resultant. You can either go by tan or tan inverse of opposite is 4, adjacent is the resultant 4.5, which will give you, so tan inverse of 4 divided by 4.5 will give you 41.6, which is 42. It's giving 41.6 degrees, so it's 42. So it's A. Okay. Okay. A man of mass 75.2 kg uses a set of weighing scales to measure his mass 3 times. He obtains the following readings. Actually, the true value is 75.2, but he is reading it as 80.2, 80.1, 80.2. It's precise, but it's not accurate, yeah? So which one, what are the statements? Which statement is the precision accuracy of his weighing scale? Not precise. No, it is precise. Not, it is wrong. So precise to 0.1 kilogram and accurate to 0.1 kilogram. Of course, precise to 0.1, but it is not accurate. Okay, it is not accurate to 0.1 kilogram. Okay, so it is precise, but not accurate to 0.1 kilogram. Okay. Which statement about scalars and vector quantities is correct? Scalar has direction? No. Scalar quantity has magnitude, but not direction. Vector quantity has direction? No, wrong. Vector quantity has magnitude? No, wrong. So B. Yeah. Thanks for watching. Please like, share, and subscribe. See you in another video. Bye.